This conference will now be recorded.
Hello, everybody. Jordan Girth here from the National Weather Service Office of Observations. Thank you for joining us for the Satellite Book Club Seminar Series. This is session number 82. Appreciate you being with us. Hope you're staying warm. And thanks particularly for those of you that popped over from the American Meteorological Society virtual meeting for this. The title, An Early History of Nowcasting Thunderstorm Intensity from Satellite. The presenter, Dr. Bob Rabin, research meteorologist from the National Severe Storms Laboratory. And our facilitator for today is Dr. Chad Gravel, Techniques Development Meteorologist at Southern Region Headquarters. Just a few reminders, as you just heard, the session is being recorded. There will be an opportunity to ask questions and get answers after the presentation. We particularly encourage members from our field offices and regional headquarters of the Weather Service to post their questions in the chat, and we will field them during the Q&A period. We also encourage you to sign in with your full name or specify your full name when asking a question if you're using a group account for your office. That'll help us get in touch with you if we need to follow up. Really appreciate that. We are looking for future presenters for the Satellite Book Club, so if you have an idea that you'd like to share with the field, please get in touch with us. We'd love to have you. And if you need to repurpose a presentation from AMS, that's even better. The training team can help create training materials that may be unavailable or point you to materials you may be unaware of. Brian Mata, the Office of Chief Learning Officer, can take your questions regarding that. Just like to thank our Tower S team, particularly Kashad Bohm and Lee Byerly, the Office of the Chief Learning Officer, the GOZAR and JPS's programs, as well as our facilitator for helping with the Satellite Book Club. A lot of work that goes on behind the scenes, and we really appreciate their efforts. Without further ado, I'd like to introduce Dr. Bob Rabin. As I mentioned, a research meteorologist at the NOAA Severe Storms Lab in Norman, Oklahoma, and works collaboratively with the NESDIS Advanced Satellite Products Branch, ASPB, and Cooperative Institute for Meteorological Satellite Studies in Madison, Wisconsin. Bob has been fascinated with observing the weather since an early age. When he grew up near Lake Michigan, his research interest in satellite and radar observations and weather forecasting and the effects of land use on climate. He helped develop the first algorithms for wind profiling in clear air from Doppler radar in the early 1980s. Bob's a repeat presenter here at the Satellite Book Club. Welcome back.
Thanks so much, Jordan, and good afternoon and good morning to everybody for joining us today. I look at this presentation as more of a tribute to the early scientists that started using satellite data to look at storms and other things, and sometimes we kind of lose track of how that all started as we move forward with new applications and research. So if we can move to the next slide, please. There we go. That's just a brief outline. I won't be covering the last item on multispectral just because of lack of time. Next slide, please. So this is an image or a photo of one of the first views of thunderstorms from space, from a satellite. It's from the TIROS-1, the very first fully operational weather satellite, television infrared observing satellite that was launched early in 1960. And the lifetime of this particular satellite was, I believe, about 2.5 months. There was a whole series of them that eventually led to the NOAA series. And this is from a paper by Whitney published in 1963. Next slide, please. It's Colorado, Nebraska, Oklahoma area. And then this is an analysis from that image and maybe others. And it's hard to see, I know, but it basically is showing the outline of the anvil clouds and then superimposed on it the location of the radar echo and spherics, which was the same concept that led to VHF receiving stations for lightning. Next slide, please. And what is evident in that figure is that the clouds are pretty obvious when you look at them, but you can imagine the excitement that occurred from those first images from satellite of storms. No one had seen them before from above. So really remarkable feat, and I can't imagine how exciting it was in that time to see those for the first time. The clouds were described as not being linear. They're more oval-shaped and highly reflective. They had sometimes sharp edges, but they're much larger in size than the radar echoes or the areas with the lightning. And then also it was noted that often there was clear sky, very clear skies, just outside the area of the anvils, and that could have been a sign of how severe it was. That was something that was proposed. Next slide, please. So this is another study done looking at looking for a relation between the size of cirrus shields and severity of the storms. This is from several cases from different series of TIROS satellites, 4 through 7. And next slide, please, by Boucher in 1967. And the conclusion of that little study was that the diameter in some ways is related to severity, in the sense that if it was much less than a certain size, 60 nautical miles, it was rarely severe. If it was greater than 150, it was usually severe. And then penetrative convection, which was observed, was not always associated with severe weather. And then this idea of contiguous areas of clear areas around were really not that common. Next slide, please. And then this next one, I should point out that there's no way that I could try to review all of the significant research, early research, in a short presentation. So I just picked out a few, highlighting a few studies that came to my mind. I'm sure there were others as well, which afterwards, if you want to mention it, that would be great. Jim Purdom did a lot of work in the early years in looking at severe weather characteristics from satellite. One of his first studies that was published was in '71 from the first NOAA series of polar orbiting satellites. And the squall lines had a characteristic appearance where they became narrow to the south. That was one of his conclusions. But you could also use the images to locate the position of both polar and subtropical jets, and then also get some idea of what the shear was with height in the thermal ridge by the amount of veering from cloud movement. Next slide, please. And then there was a series of studies that came out of the third in the series of ATS satellites. So those are the first geostationary type satellites, application technology satellites. And these are some of the general conclusions. Early detection of squall lines is compared to popping up on radar. Often the severe areas seem to be in the southern portion of the convective clusters. Growth of the anvil, there was these observations and hypotheses that when there was a pause in the rate of expansion of the anvil seemed to be when tornado occurrence happened when it did. And then McCann's study linked the collapsing storm tops to downdraft formation and tornado formation. Next slide, please. So And then next slide, please. So convective initiation, Jim Purden did a lot on that, as many of you I'm sure know. And so in this particular monthly weather view paper in 76, he published some of these results. And we'll go on to the next slide, please. So yeah, he noticed the importance of storm initiation and maintenance from boundaries. I think that was the big breakthrough there. And the satellite images could be used to very precisely identify the locations of boundaries compared to other data available. Surface data didn't have the resolution, and I don't think radar data at the time was sensitive enough to pick up boundaries so well. But he also identified cases where there was merging or intersecting of boundaries that seemed to lead to new convective initiation, given you had favorable conditions. Next slide, please. And that was all qualitative. And next slide, please. So the next section here, we're going to delve more into observations that use the infrared window channel observations of these clouds. And Charles Anderson, the University of Wisconsin-Madison, did early work in the late 70s. This is from, I think, the 13th Severe Storms Conference, looking at characteristics of cirrus plumes of severe storms. And what he observed there was they were displaced to the right of the ambient wind. There seemed to be anticyclonic rotation at the anvil top in general, with spiral bands somewhat similar to hurricanes. Next slide, please. And then overshooting tops. Don McCann in '79 in the same conference published a report on a study and noting these observations from aircraft that Fujita Umenhofer had observed a few years earlier concerning possibility of collapsing tops related to tornado formation. His conclusion is they did not cause the tornado, but the collapse might be related to the acceleration of a gust front or enhanced downdrafts, I guess, and occlusion of a mesolow with strong surface outflow, bow echoes, etc. Next slide. And then in 1980, Bob Maddox did quite a bit of work, breakthrough work on in defining what's now become known as MCSs or MCCs in this case, based on the characteristics of the anvils from satellite images like you can see here. The next slide. He quantified to some extent the characteristics of those cloud anvil systems from the IR imagery, and came up with some criteria to define MCCs. So cold tops colder than -32, size greater than 100,000 kilometers. The eccentricity had to be such that they're rather circular, and they had to last for at least 6 hours. And that was something that I think was really well appreciated from satellite imagery, at least quantified until that time. And they do produce a wide variety of severe weather during their lifetimes. And then maybe more important to all this, he pointed to how difficult they are to forecast, and that remains so today, because they tend to occur where there's weak upper level support, like near an upper level ridge, and low level warm air advection plays a role. Next slide, please. So growth rates, we're all familiar, I hope everybody's familiar with the prop severe and the use of cloud top cooling rates in identifying potential severity of a storm. That work actually came out of the next slide here. There may be some other studies around that time as well. from Bob Atler and Doug Fenn. This is published in '79. Notice that those curves, they're probably hard to see, are showing the expansion, or it's on a logarithmic scale in time of different cloud top temperature thresholds. So basically, there's an expansion of the colder area, very rapid as it's growing. The other thing to note here is that this used SMS-2 data. SMS is a synchronous meteorological satellite series, geostationary satellites, which then GOES 1 was launched shortly after this. SMS-2 was launched in '75, early in the year, and GOES 1, I believe, was in October of '75. But note that the study actually used 5-minute intervals. So we kind of thought about rapid scans coming, at least I did, rapid scans not being available till the '90s. But there were these early studies that had, at least experimentally, relatively rapid scans back then. Next slide, please. So these were the conclusions from the study. Tornadoes would occur during or after the most rapid expansion in 7 of the 8 cases. There seemed to be a statistical relationship to severe weather. Colder and more rapid growth were more likely to be severe. They pointed to a potential warning lead time of 30 minutes. Divergence in vertical velocity twice as much for severe storms as non-severe storms. Limitations, these results based on a limited sample, and existing anvils can obscure new storm growth, and that's of course still a problem today. It's not going to change. Storm top heights were underestimated from satellite as compared to radar. Next slide, please. So another interesting study that used data from the first GOES was that from David Reynolds in 1980, looking specifically at damaging hailstorms. And the curve on the right there basically shows how the cloud top temperature eventually gets colder than the equilibrium level and reaches its peak there about the same coldest temperatures or deviation from the equilibrium level about the time of the largest hailstones. So this is based on, I believe, the Henry experiment, hail experiment, Montana, if I remember correctly. And then it starts warming. Next slide, please. Based on 9 storms, cloud tops colder than tropopause, infer vigorous updrafts. Would expect a better relation for hail than for tornadoes using these type of cloud top techniques, because there's so much other factors in the nearer the ground related to the formation of tornadoes. And also this was valid for large, long-lasting hailstorms of 3 to 5 hours. So next slide, please. Oh, one other note on there. So access to satellite data in a digital form was limited back then. It was qualitative, looking at images. So it was pointed out that this and other studies that using the proper enhancement is going to be important to identify, well, is it colder than the tropopause, things like that. Now this study by Adler, Marcus, and Fenn from '85 actually tried to quantify a severe thunderstorm index, used SMS-2 and GOES 1, the 75 data, the 5-minute data, and that histogram, the stippled columns there are the occurrences of severe storms, and the unfilled areas are non-severe, and then the index is increasing from left to right. It's a relative index. And it shows if the index is less than 4, roughly, none of the storms were severe. If they're greater than 4, at least 50% were. Next slide, please. And this slide will show some of the highlights from that study. So they combine parameters of related to updraft intensity or inferred from cloud top ascent rates, expansion rates of isotherms. They combine it into this one index. And they also noted the V shape, which I'll show just after this, with an embedded warm spot. And then limitations, identification of cloud tops is limited to certain stages, and the resolution of IRs it's not as good as reality. So cloud tops are warmer than they really are, and there's this ambiguity in height from cloud top temperature. Next slide, please. We still have those problems today. So the enhanced V structure, next slide. So this study in the Severe Storms Conference 10th in 1977, we're going back in time a little bit, from Mills and Ashling, tried to quantify some of these patterns of, and you can see of enhanced V-like signatures with warm spots on the anvil. And it was hypothesized that those warm spots occurred due to near tropopause penetrations, and that was confirmed by radar observations. And the warm spots themselves could have been due to higher emissivity of the hydrometers above the updraft, stratospheric cirrus, and rapid sinking. Next slide, please. So that was in 1977. And then in 83, Don McCann published this formal paper on the enhanced V, the Monthly Weather Review, and there's a nice black and white gray shade image of it there with a cold spot and a warm spot. Next slide. He used a relatively large sample, 884 cases, which is quite a few. And conclusion was that these patterns were the result of the interaction of winds and the overshooting tops, which I think still exists today as a major hypothesis, without being too detailed about it. And so that requires strong upper level winds in order to get that to happen, relative to the movement of the updraft. Many severe storms do not have enhanced Vs, so the probability of detection just using the enhanced V structure was relatively low, only 25%. False alarm rate was similar to other methods, was about 31%. Lead time, if for the cases that did have enhanced Vs, was about 30 minutes, and again requires proper enhancement of the images to bring out the structure. Next slide, please. There we go. So this paper by Adler and Mack in '86 in JAS was, to me, really interesting because they really went further and used a simple one-dimensional cloud top parcel model and compared to the satellite observations. And what's shown there are these three classes of convective overshoots, basically, class 1, 2, and 3. The top one, there's basically there's a monotonic lapse rate above the tropopause, and the updraft goes up, penetrates into the stratosphere, and then symmetrically comes down on the sides. The other two are sloped or slanted. Let's go to the next slide. So kind of a fundamental, I would say, understanding of how these different patterns might manifest themselves depending on the shear, but also the lapse rate above in the lower stratosphere. And what was also unique about this study is it actually used stereoscopic observations from GOES to estimate the heights, May 1979. And here are the three different classifications: concentric, monotonic temperature versus height profile in the stratosphere. Warm-cold couplets then form when you have a displacement. Case 2 is when you have an isothermal layer, and then you get an offset when it's there's an inversion with strong mixing. And they also noticed the close-in warm point, and hypothesized that was due to substance undershooting, and they documented it again with the stereoscopic height calculations of the cloud top. So in other words, the updraft penetrates into the stratosphere, but then downwind, it sinks back down and undershoots. So it's part of the same sort of oscillation up and down, and that's where the subsidence and the warming occurs. Next slide, please. There we go. And then this paper by Jerry Heimsfield and Roy Blackmer in '88 does some further observations, detailed observations of the enhanced V or U-shaped structures and the location of the different cloud top temperature anomalies. So on that one on the left, you see the coldest point, and then downwind of it, the warmest point, and then you have a field warm spot further down, and then there's a schematic on the right that shows some of the wind patterns of the wind flowing through and around the overshooting top area. Next slide, please. And so second distant warm spot is often observed. The width of the V is related to the spacing of the cold and distant warm spot. And they also concluded that the temperature difference between the warm and the cold spots were related to the amount of overshoot, which makes physical intuitive sense anyway. You have more of a vertical strength and vertical velocity, so it's going to go up further, gets colder, and then sinks back down further and gets warmer. And then ingredients for the V shape: strong shearing of the tropopause and intense updrafts with overshooting tops. Next slide, please. And then they elucidated various hypotheses regarding these manifestations as well. And then limitations, again, the IR pixel resolution was well recognized as an issue. And then unknown temperature and ice crystal structure to relate to emissivity. And then complexities in multi-storm structure. 3D models seem too simplified. We all know that too well. Next slide. So in summary, there's a long history of satellite research that started basically in the early 60s. So that's 60 years old now. And it became a hot topic for research in the meteorological community through the 80s, 70s, and 80s. And then it kind of petered out, at least in my observation. Not to say there weren't any studies at all, but people were really excited about it, and then the ball kind of dropped. And I think some of that may be due to limitation of operational access to these ideas and use of the satellite data in a timely fashion and maybe a digital way. But the other effect is, I think, the advent of Doppler radar, which was born here at NSSL, And you know, by the late 80s, that network was being developed and through the 90s, and certainly had a strong beat on being able to identify directly the circulations in the storms themselves associated with mesocyclones, downdrafts, outflow boundaries, and such. And resolution limitations was a factor. And then the greatest impact of the imagery really is always, at that time, all qualitative. It was certainly indispensable, I believe, in nowcasting and forecasting, but it was used strictly qualitatively. Some of these techniques, like that severe index that Adler and Fenn present, I don't think that was ever really tested or used operationally. And then I'll conclude with the last slide here. What is the future? We know what's happening now. We know what's being proposed in the next maybe 20, 30 years in terms of the next generation of GOES. But where is the real, is there going to be a real next step breakthrough at some point? I don't know. I mean, I don't see anything really fundamentally coming up that's going to fundamentally change anything. Maybe having radars on a geo platform, that's probably won't occur in the next 40 years, but I could see something like that, you know, really revolutionizing things. But that's just my own personal opinion. So I will turn it over to the moderators here, and hopefully you enjoyed some of this, and it was useful for you to see some of these slides.
Yeah, thanks, Bob. Before we get into Q&A, and for those of you who can stay, please stay for Q&A and put your questions in the chat box. I need to remind you that a week from today, on February 3rd, at 12:30 Eastern Time, John Evans and Lee Byerly from the Tower S team will discuss new content and updates in Tower S RPM version 22. If you have any questions, you know, or feedback about the Satellite Book Club sessions, feel free to reach out to the Tower S team, Lee Byerly, Kashad Bauman, for questions, again, about the Satellite Book Club. And then with that, let's get into Q&A. So, you know, Bob, one of my big takeaways is that, you know, as I was thinking about this a little before, you know, just before your presentation, that it's always good to remember where we came from so that we can appreciate what we have today. And I think for a lot of operational METs, it's even those that can remember before Go 16, Go 17, that it's really hard, right? We take it for granted almost. So I'm wondering, before we get into some specific questions, I'm wondering what your thoughts are on that. Do you think that we take Go 16, Go 17 for granted? Is that one of the kind of like the reasons why this is kind of passionate to you, to kind of like show the history of severe storm detection?
Well, I think that's a good general question for any technology, and I believe that once you get used to something, or you were born with it there in some sense, you do take it for granted because it's kind of like, well, it's there, you know. And you could, you know, say something about cell phones or you know, television for that matter, that, you know, or kids today, you know, taking for granted they can just stream stuff that, you know, obviously wasn't possible a decade ago.
Right,
and I think it's
dial-up internet too, right?
Yeah, right. Or no internet, you know, one time. So, you know, and I think it's true with this too, that yeah, you can't really, you can imagine, unless you really think about and imagine what life was like without it. And then, yeah, but I also saw, I think, my experience being around others, looking at satellite data and radar data and such, was that they saw it and they liked it, but they said, "Oh, couldn't it be better if we you get these every 1 minute, or looking for more." But
Mhm.
now we kind of, I think, almost, in my opinion, kind of plateaued in a sense on that, and yeah, okay, maybe we can double the resolution, in the next series. Obviously, we could go to 30-second, but I'm not sure we'd gain anything. So yeah, it's just a more philosophical thing. But the other thing, there's so much more data now, and data overload too is a concern that you've got to pick and choose and what you're going to kind of focus on as being most valuable, and then the machine learning, and that's new in the having automated algorithms where you don't even have to think anymore, which I
Yeah,
think is
exactly. And,
dangerous.
and that's where I think even though we have like a wide array of satellite algorithms, um, I really think the future is in machine learning and using this data. Like if you think about like Lightning Cast, this pretty immature because of time product that Mike Pavlonis, has developed, that like it's remarkable how fast that spun up and how mature it is, as in how reliable that probabilistic product is. And it's using satellite images. It's basically being trained on what the data looks like, and there's a lot of power in there. It's almost like if we can imagine something now, you know with machine learning, artificial intelligence algorithms so readily available, it's almost like anything's possible. It's pretty remarkable. I think to me that would be the future, of that data. Um, another thing that I kind of thought about, like, was like I still, in my opinion, like, and this isn't me per se, but I hear this a lot, that forecasters still have a hard time, right? They have a hard time integrating the satellite data in the forecast warning process. So like there's been a big push in the last few years on the mesoanalyst. Like that person is really analyzing the satellite imagery along with the environment to provide good on-demand guidance to the warning forecaster. But the radar still king, when it comes to that. Especially like I know there's like some data sparse regions across the US, but they're pretty limited. Like there's radar data is like it's great, especially east of the Rockies where most of the severe storms happen. So I guess my question to you is like, what are your thoughts about radar data versus satellite and integrating the two?
Wow, that's I remember Maddox and others talking about that very thing back around 1990, roughly. And it's been the challenge since, is yeah, integrating them together. They're obviously two different things, and um, marrying them together isn't always possible in a full way, but
Mhm.
certainly being able to, I think, I feel strongly, yeah, to put them into the same georeferencing, so you can look at them somewhat in the same perspective, is very valuable. And to look at them separately is a shortcoming in general. How to best, I don't know if we've reached a peak in being able to blend them together. Um, they both have limitations, and
Mhm.
yeah, it's a difficult thing, like Prop Severe I'm looking at, and it's doing that in a maybe in a way where you bring together, you're tracking a cell, say, and you've got automatically, and you get time series of different parameters from both radar and satellite. Well, the radar, the beam height's changing as the storm's moving, and you get the values of low level shear, what have you, that are going to be to some extent influenced by the sampling, which is changing in time, and then you're trying to look at those trends and integrate them together with trends of the cloud top structure. So I think we're doing the best we can in trying to blend them together in the most meaningful way right now. I'm not sure we can get any better at it, but I think it's important.
Yeah, I mean, yeah, absolutely. And like Prop Severe to me, like, to me, that's it, right? Like you're integrating environmental information, satellite information, and radar data, right? You're trying to do with Prop Severe what the human really struggles with. It's again, it's remarkable, technology, for lack of a better word. There's some comments in the chat. I don't really see. There's one question here, and we can close with that because we are kind of running out of time. And that question is from Steve Goodman, and he was wondering, what's the trade-off between more ground-based observations, profilers, radar, CASA radar, versus satellite cost? And that's what he has there, what he asked. Do you have any comments on that?
I sure do. I in terms of the actual dollar cost, I can't say. Of course, satellites are very expensive, but obviously any ground-based equipment put into a large network is going to be pricey too.
Mm-hmm.
But I think the benefit of doing that is going to be multiplied maybe non-linearly by having more ground-based observations. I think those are critical. I personally just don't think satellites, at least as we have them now, have the needed capability to do the low boundary layer profiling, for example, and monitoring near the ground for certain types of high impact weather like tornadic storms. And so the cost may be somewhat, although it has to be justified, obviously, that the payoff, if it's in terms of life saved or whatever, is going to greatly outperform the cost paid, or the benefit will be better. I think the same argument can be made about, and I've always argued this with profiling with Raywin sounds. We haven't really upgraded in terms of upper air soundings for forever, it seems like. And I think yes, there's a cost involved with maintaining those and expendables and all that. I think there's a value of using manpower, using the people to be on the ground taking observations, rather than everything is just going to be done automated from space. It's going to solve all our problems. I take a negative view of that. That's my own personal opinion. I maybe talked too much about that question, but
no, I think it's good to hear your insight. I thought I had a follow-up, but I guess it kind of slipped me. So with that,
one thing, can I really quick? Yeah, one example of that is ground-based cameras. I mean, there's a lot of course, cameras around, road cameras or whatever, that are being used for observations near the ground. But why not have a bigger network of ground-based satellites, if you want to call them, looking up and getting cloud movement and stuff? I mean, that's all that could be done too. It's going to cost money, but it certainly would augment the other end of the observational trail there.
Yeah, and one of the things that I remember what I was going to say was a few weeks ago we had a satellite book club about the benefits of the GOES-R on the tropical program, and they're estimating that as $9 billion alone. So like, I mean, that almost pays for the GOES-R series in a way, right? If we think about it like that. So it's pretty interesting on you know, that discussion I've appreciated in the last year or two. So Bob, thank you again. You know, with that, I'm going to turn it over to Jordan so he can kind of close us out here.
All right, thank you, Chad, and thanks again, Bob, for that great presentation. Always good to understand our history of how we got to where we are today and confronting some of the challenges related to the use of weather satellites in the warning process at the Weather Service. So as has been mentioned, on Thursday, February 3rd at 12 noon Eastern Time, John Evans and Lee Byerly from our TowerS team will provide an update on the TowerS RPM version 22. So hopefully you'll tune in then to hear what the latest and greatest will be part of AWIP soon. And also, if you have any questions related to the configuration of satellite products in AWIPS, that TowerS RPM, or the Satellite Book Club, please get in touch with Lee Byerly or Kashad Bowman. Their email addresses are there on the slide, or feel free to drop into the NWS chat, Tower-S. With that, we really appreciate your time today. Once again, thanks so much, Bob and Chad, for being with us for the Satellite Book Club. And I hope you'll join us next week. Take care, everybody.